Well, greetings, everybody. So somebody sent this question in today, and I think it's from the quiz. But regardless, I did copy the question and include it here with my work and my setup. And to give you a little context, so far I have given you this video right here, plus some others, which explains that when we solve a linear programming problem, we want to maximize or minimize some function subject to the points in something called a feasible region. Okay, if the feasible region is bounded, like closed on all sides, like this one is, then the original function, whatever it is, okay, let me back up a little bit. You know, whatever this z function is, z is equal to something x and something y, it will have a maximum and a minimum with respect to all the points in the feasible region. Okay, all right. Now, what's different about the one that I want to show you now is that it says that there's no maximum value. I'm going to talk about why that is. Okay, but otherwise it is like this other one. Okay, there's some function that's given that we're going to find either the minimum or maximum or both, and it's subject to these constraints, and these constraints all together make some kind of graph, and that graph is called the feasible region. And we just want to see, of all the points in the feasible region, whatever it looks like, okay, which one gives you either the maximum or minimum or both, of whatever this objective function is that you're given. Okay, so in a linear program problem, you'll have something to maximize or minimize. That's the objective function. And then you'll have all these inequalities, which are the constraints or the feasible region. Okay. All right. So what's different about this one? Why does this function here have a minimum over the constraints, but not a maximum? Okay. Well, let's talk about this in a way that is applicable to any linear programming problem. Okay. So I want to find the maximum or minimum values of this, subject to all the points in this region called the feasible region. So I would start by trying to look at the graph of the feasible region. And there are lots of ways that this can be done. You might have a graphing calculator. You might use something online that graphs it for you, but you know, we'll have to have a look at it. We'll have to see what it looks like. Okay, so the way I'll show you, because I'll assume if you have a graphing calculator, then it's doing all the work for you anyway, but one, like, you might not have a graphing calculator, and two, I think you should, even if you did use one, you should know how to draw the graph. You should know what the graph is supposed to be. The way I would do it, I mean, there are lots of ways, but I would take each of these and solve it for y, and then graph that line that I get. Okay, so like 4x plus 3y greater than or equal to 12. If I solve that for y, it says y is greater than or equal to 4 minus 4/3 x. So part of the feasible region is all the points above the line 4 minus 4/3 x. Okay, so in other words, if I graph the line 4 minus 4/3 x, which you see right here, part of the feasible region is all the points above that line. The reason is because it says y is greater than or equal to 4 minus 4/3 x. All the points on the line are the points where y equals 4 minus 4/3 x. The points above the line are the points where y is greater than 4 minus 4/3 x. Okay, so that would be part of it. Then to take the other one, solve it for y, I'll get y is greater than or equal to 2 minus 1/3 x. That's this line right here. Okay? So for the feasible region, I would need, likewise, all the points above the line y equals 2 minus 1/3 x. Okay? Now these last two that were given, x greater than or equal to 0 and y greater than or equal to 0, well, x is 0 on the y-axis. So x greater than or equal to 0 is all the points to the right of it. Okay? Where are all the points where the x is greater than 0? They're all the points to the right of the y-axis. What about y greater than or equal to 0? Well, on the x-axis are where the points are where y equals 0. So all the points where y is greater than 0 are above that. So what you see here shaded in green are the points above this line above this line, right of the y-axis, and above the x-axis. So that's what this is. It satisfies each one of these. Above this line, above this one, right of the y-axis, above the x-axis. Alright, that's the feasible region. Now, what's different about this one, now that I've graphed it, is it's not bounded. It just goes forever out this way. Compare that with this other one in my other video that I've already posted. It's bounded. Like if you graph each of these in the same way that I just described, it's like closed off on each side. In that case, this objective function that we're trying to maximize or minimize, okay, is going to have a maximum and a minimum at the corner. You just have to check each corner point. One of them will give you a maximum, one of them will give you a minimum. Okay, that's how it works. Now, whenever we have a feasible region that is not bounded from above, like this just goes forever out and up, like there's nothing on top of it up here to like close it off, then there won't be a maximum for the objective function. So that z is 3x plus 9y, it won't have a maximum value. It will have a minimum, but not a maximum. Okay, so, well, okay, how do you find the maximum and minimum? You know, if like technically, what we're asking is if you have all the points in the feasible region, which one gives you the maximum or minimum in the objective function, whatever you're looking for? That's a lot of points to check. I mean, can you imagine if we had to check every point in this feasible region? That would be impossible. You could never do it because there's an unlimited number of points in here. There's this one, there's this one. I mean, you get the idea. But this technique is such that it guarantees that the maximum or minimum, whatever you're looking for, has to be at one of the corner points. So you just have to check the corner points, okay? So what I would need to do next is that realizing that because this is not bounded above, this will have a minimum, but it won't have a maximum. That minimum will be found at one of the corner points. So for this region, the feasible region, there's 3 corner points, A, B, and C. So my answer, the minimum value of this objective function must occur at one of the corner points A, B, and C. So next, naturally, I will want to figure out what A, B, and C are. Okay. So here's how we do that. Point A is the intersection of x is equal to 0 and y is 4 minus 4/3 x. See? Point A. X is equal to 0 is this line. 4 minus 4/3 x is this one. Okay? So I look for a solution out of these. And the way that I do that with this is if this first equation says x is equal to 0, then I accept that as the truth, that x is supposed to be 0. And then I plug it into this other one. And what do I get? Y equals 4 minus 4/3 times 0. It's telling me y. If I plug in the x, I get the y. So the intersection must be x is 0 and y is 4. Okay, so that point is 0 and 4. So now I know point A. That's one of the corner points. Let's look at point B. Point B is the intersection of y is 4 minus 4/3 x and y is 2 minus 1/3 x. The way that I solve that, the way I find the intersection of this line and this one, in this case, is I can set them equal to each other. Okay? So in this first one, when I was told that x is equal to 0, then I plug that into the other one. But here I don't have that, so I can set the equations equal to each other and solve. That will tell me their intersection. So I set them equal to each other. I move the x's on one side, numbers on the other. I solve, I get x is 2. Once I know that x is 2, I know the x coordinate of the point of intersection. I can plug that in to either of these to get the y. It doesn't matter. I happen to take this one. I took 2 and I plugged it into this one. I could have used the other one. Makes no difference. I put it here. I get this. I do a little math. I get 4/3. So, point B, where these two lines intersect, is 2 for x, 4/3 for y. So last, point C, last corner point for our feasible region, is the intersection of 2 minus 2/3 x, it's this line, and y is equal to 0. this one. Okay, so we need to intersect y is 2 minus 2/3 x and y is equal to 0. Now, what I can do there is, if I'm working with the assumption that y is 0, if that's one of my equations, it says y is 0, then I can take that and I can plug it into the other one. It's a known value of y. So I do that. It looks like this. Okay, I solve it for x, I get 6. So point C is 6 for x, 0 for y. 0 for y, 6 for x. That's this point. Okay, now I told you that we're looking for the minimum value of this function over this feasible region. And it has to be at one of the corner points A, B, and C. We don't have to check all the other points, just the corner points. I now know what the corner points are, so naturally I put them into that objective function. I look for the minimum, okay? So point A was 0 for x, 4 for y. That gives me, out of this, it gives me 36. Point B was 2 for x, 4/3 for y. I put in this, gives me 18. And point C was 6 for x, 0 for y. I put it into this, it also gives me 18. So, you know, whatever the minimum value that this is going to take is going to be here. And so it would have to be 18. That's the smallest number I got there. Even though I got it twice, I mean, that doesn't matter. You know, it was guaranteed to us that the minimum value that this is going to take over the feasible region is going to be at one of the corner points. I checked them. 18 is the smallest number I see. So that's why I can say that the minimum value is 18. Okay? All right, why did we say there was no maximum value? Well, because when you graph the feasible region, okay, when I graph each of these inequalities, I'm looking at this and I see something unbounded from above. There's no top to it. There's no line that blocks it off on the top. That's what we mean by unbounded. For that reason, there will be a minimum for the objective function, but there won't be a maximum.